Welcome everyone. Today I want to speak about importing data into Neo4j, and this is a topic which is really dear and near to my heart. So I've been importing data into Neo4j since 2008, I think, and I have many terabytes of databases imported and many billions of nodes and relationships imported into Neo4j over the course of all these years. As Alex said, I'm developer evangelist or developer advocate at Neo4j, and I helped a lot of people in the past to get their data from a variety of sources into Neo4j, and I hope I can help you too to be efficient and quick in doing that. So I firstly want to quickly talk about the webinar series. We are already at the third installation now of the series, and one more to follow. Want to talk about different ways of getting data into Neo4j, quickly refer to things how you can get data out of your relational database, show you some concrete examples and with demos, and we do some Q&A at the end. So this relational to graph webinar series is something that we've wanted to do for a long time, helping people to get up and running with Neo4j quickly when you come from a relational background and have relational database experience. And starting with an introduction overview on the topic, my colleague Ryan did the first webinar. Then I ran the modeling webinar for relational to graph. So what is the difference between relational models and graph models, and how do you get from A to B, and what's a good way of doing that? Today we talk about import, and next time in the next webinar we will look into querying your data in a graph. So compare SQL with Cypher and see some really hard SQL queries, how easy they can be in Cypher, and also how performant it will be. Why are we doing this whole graph database thing, right? I mean, database is a database, but actually not all databases are created equal, as you probably know. And each database has its own unique advantages and sweet spots. And interestingly, despite the name relational, which comes actually from relational algebra and not from relationships, relational databases are not so really good at handling complex data with a lot of connections between your tables or entities. And that's because the relational model knows only one kind of type of data structure, which is a relation or a tuple or a table. And you have to model everything with tables, and there's no concept of a connection as such. There are just keys in your table, which might be primary keys of another table. So when you query your data, there's actually nothing that kind of makes it easy for the relational database to find the connections. And that's why it has to really find matches between primary keys and foreign keys. And the more data you have in your relational database, and the more joins you have in your query, in your SQL query, the more complex and costly it gets. And that's something we've seen a lot in the past when I was consulting myself with relational databases, that a lot of complex queries take a really long time. And another aspect that's really hard or annoying to do in relational databases is I want to evolve my database really quickly while I'm developing an application. So that means I want to add new types, I want to add new properties, I want to add new relationships on the fly. But I always have to go and update schemas and manage schemas and fight with my DBA if he allows me twice per week to update the schema or something like that. And that makes it kind of really hard to do the interesting things in a relational database. In a graph database, you actually stay in the same model all the time. So you start with a kind of conceptual model on a whiteboard. You build your object model, which is also the same structure as your conceptual model. And then you don't have an impedance mismatch to map your data from the object model into the graph model in your database. And then when you pull the data out again out of the database, then your graph visualization looks exactly the same again. as your object model and as your conceptual model. So that's first really nice thing to make it easy to model and evolve your domain. It's also easy because there's no required schema, so you're free to add new data, new relationships, and other things on the fly. And relationships are actually treated like data. They are not something special like in a schema or so, but they are just like changing a name. You can also add new relationships and new types of relationships directly. And graph databases were actually initially created to solve this join performance problem. So because what they do is actually an optimization that you could also do otherwise, but graph databases do it out of the box. What they do is they pre-materialize relationships, connections between entities and store them with each entity. So each node, each element in our graph database has a list of all its connections grouped by direction and type and some other properties. And then kind of finding these connections, kind of the join operation is a really fast operation because it just has this list of already existing pointers to the other nodes, and it can just follow these pointers. So it's way faster. Also, in a graph database, what you do is local queries. So you have starting points, and from those starting points, you actually navigate around the neighborhood of those starting points. And it also means no matter how much data you have in your database, if you only kind of walk around in your neighborhood, you actually don't care much else is there. Which allows you to have really a lot of data in your graph database and still have highly performant queries. Okay, that was kind of the why we do this whole graph database thing aspect. I quickly want to introduce you to some of the APIs and means of importing data into Neo4j, some tools and some tricks. So something we started about a little more than a year ago is load CSV, which is a new Cypher keyword. Cypher is Neo4j's query language, which is similar to SQL. And this load CSV is a capability that allows you to load CSV files from HTTP URLs or file URLs into your database. Each row of the CSV will be made available to your Cypher statement. And then from those rows, you can actually create or update graph structures as you like. So you can find nodes, update data there, you can create new nodes, you can create new relationships, and so on. So it's a really powerful way of converting kind of flat data, meaning CSV files, into graph data and connected data. And it works with kind of CSV files that have just a single table in them, but it also works with CSV files which contain a fully denormalized table or a join of several tables. You can use both. So you can also convert data on the fly, you can filter, you can aggregate all these things while loading the data in, which is really nice. Or you can also destructure input data. So when you have more complex input data, then you can also kind of split arrays and reach into the array to pull out a single value or something like that, or iterate over a certain list of attributes and filter out some that are interesting to you and then store them as an array property, for instance. So there's a lot of capability there. You can control the size of transactions so that you don't run into memory issues with a certain keyword. And you can run it as well via Neo4j shell, not just with Neo4j browser, which makes it easy to script imports like that, because you can just provide a file with all the load CSV statements that you need, and then run this Neo4j shell with this file. This is also what I will show later. The other thing we added to Neo4j, I think a while ago, 4 or 5 months ago or something like that, is an scalable input tool for bulk inserts. And what it does, it takes, again, CSV files and scales them across all the CPUs that you have and all the disk capacity that you have by putting it into a kind of stage architecture where you kind of each input step is parallelized if possible, and then they form kind of a staging step-by-step input scheme, and use also some tricks for compression and in-memory compression, and also for creating the graph structures. And it's really cool because it's really fast, so it can do 1 million records per second. And it can also really import large data sets, so several billion nodes, relationships, properties without problems. What you can also do is just use the Neo4j APIs to run Cypher statements yourself. So you can create, update, merge statements with Cypher via the APIs that we have. So one is the HTTP endpoint, which is available to all drivers, and you can also use it directly from an HTTP client or an HTTP library in your language. And then you can get data from somewhere. That can be a relational database, could be a web API, could be a directory structure, it could be a internal in-house data store or an BI system or whatever. You can pull the data out and convert it into parameters for your Cypher statements, and then you just send them in. And then you can also batch them and control transactions. And since Neo4j 2.2, this also works really well with highly concurrent writes. So when I ran the first test there, I could insert in total 1 million nodes at relationships per second with highly concurrent Cypher statements, which was really nice. And so you can do that with a lot of drivers, but if you also have a JDBC driver, that means if you have like an ETL tool or another tool or a Java program that already uses JDBC to write data somewhere, then you can also use Neo4j's JDBC driver to write data to Neo4j, because Cypher statements are just query strings like SQL as well, and you can provide parameters to them as well. Another option is a Java-based implementation of an importer, which you can also use, for instance, to generate data on the fly. So you don't have to kind of load data from somewhere, but you can just generate it on the fly. And there you would use Neo4j's Java APIs, or Cypher via the Java APIs would run on the JVM directly, talking to Neo4j without any network in between. You can also run it highly concurrent and have full control over transaction management, transaction logs, and so on. And you would kind of create either nodes and relationships directly and update their properties and so on, or you use Cypher as well. So that's as you want it. And you can also implement this as a Neo4j server extension. That means you can install it into your Neo4j server, secure it, and then you can, for instance, post data to these endpoints, and this data is ingested really rapidly, and you could even connect it to message queues or something like that to import the data. So you can also load arbitrary data, so it's not limited to just relational databases. The next one is the API behind the bulk loader. So this bulk loader that we have actually uses a Java API underneath, and you can also use this directly, which is pretty neat, because you then get the highly performant import staging architecture for free just by sending data to this API. And what you do is you just create streams of node and relationship data. So you can kind of have an iterator of node data and relationship data, and then it takes care of that to ingest it in concurrent, in parallel. And that works actually pretty well. It's a bit more work, but then you get a really high performance importer for your data as well. It handles different means of ID generation, ID mapping, conversions as well, and it also provides access to a highly performant CSV parser, which can then be decorated for modifying intermediate results and so on. So that's also really useful. So we can import with Cypher and load CSV. It works really well, up to 10 million records, I think. You can import 100,000 to 100 million records, not per second, but in total, transactionally really well. And if you want to import billions or tens of billions of records, then you would use the bulk loader or bulk loader APIs. And depending on the hardware that you have, you can import really like up to 1 million nodes and relationships per second. So that means you have a really fast SSD because it will be saturated pretty quickly on a rate of SSDs, many cores. So because both the concurrent write load in Neo4j as well as the bulk importer use as many cores as you can get. Actually, you don't need that much RAM, so it already works from something like 4 or 8 gigabytes. And if you have more, then it can kind of hold more intermediate state in memory. It makes sense to have data files local, so you don't want to pull them over the network to import them all the time, especially if you run it multiple times, then it's kind of a bit annoying. And you can compress them as well, so it can also handle compressed files. What's also helpful is if you load data from a relational database directly to have a highly concurrent connection to the relational database. So because what I've seen in the past is that many relational databases actually don't support really well kind of sucking out a lot of data in a short time, and then it stalls actually in loading the data out of the relational database. So for instance, for one customer, we had a really large social network, and they dumped it out of their MySQL cluster, and it took like 3 days or so to dump it, and then only 3 hours to import it into Neo4j. So that was kind of really surprising. And then also when you write to disk, try to disable virus scanners and check your disk scheduler on Linux so that you get the highest disk performance as well. And set some options that make it also really fast. How do you get the relational data? There are also some means of doing that. So I think all relational databases allow you to dump both whole tables, whole databases, as well as query results to CSV. In Postgres, it's just a copy function. Other databases have similar functions as well. So that should be really easy. The problem is, of course, then in many cases, then the CSV file resides on the database server, so you have to download it from there. That could be a challenge. You could also access your relational database with a database driver like a JDBC or ODBC driver or another driver to pull out the datasets that you want to pull out. For instance, also if you want to set up a syncing mechanism between a relational database and Neo4j, then it makes sense to kind of regularly pull certain tables, for instance by timestamp or by a certain updated flag or so, to pull the updates into the graph. Some databases also offer built-in endpoints, so HTTP endpoints or similar, or XML, SOAP endpoints that you can use to pull data out. Or they can be integrated with such APIs. So for instance, at Heroku, there's this concept of Heroku data clips, which is just you take a SQL query, create a data clip from the SQL query, and then this data clip provides you an URL, and from this URL you can pull the data as CSV, as Excel, as XML, as JSON, and as text. And it automatically refreshes the data when it changes in the database. And we can use this endpoint, for instance, directly with float CSV to load data into Neo4j, which is really nice. So because it's auto-updating on the other side, and we can then just get the data that we want. Or you can use existing ETL tools like Talent or others, or Kettle, to use in Neo4j JDBC driver to write data to Neo4j. And that works also really well for existing tools. So if you have already ETL tools in-house, then that's also pretty straightforward. Some of them even have a native Neo4j integration like Talent, and then you can use that as well. Okay, so much to that. How would you go ahead and input your data? So I want to show you with float CSV how you can import address data. For the bulk loader, I want to show you the crime dataset, Chicago crime dataset. And then I wrote a few weeks ago a proof of concept relational import tool that just uses JDBC to connect to a relational database, extracts the schema information from a relational database, applies some transformation rules, and then imports the data using the bulk importer API into Neo4j. Okay, let's get started with that. Load CSV. Load CSV is quite interesting because it's very powerful, but in general, just a word of caution, CSV data is mostly messy data. So we've had to learn it the hard way when we developed all these input tools, that you can't really expect an ideal world where everything is nicely formatted, well quoted, nicely delimited, and there's always messy data in there, right? So people have CSV from a source that doesn't, for instance, set quotes right, or there's a byte watermark in the beginning, which can trip up things. Sometimes you have CSV data with binary zeros in there, where some CSV readers get hiccups, or non-text characters as well. Then you have inconsistent line breaks, where you have line breaks in between without quotes around them and stuff like that. Then you have headers which are inconsistent with data. So you have a header with 15 columns, and then you have data between 7 and 35 columns or something like that. You have special characters in non-quoted text which are not handled well, and then also kind of unexpected new lines, especially in unquoted text fields. It's really high. And stray quotes is a really annoying source of problems. So especially if you store data from social media also, and people put smileys and stuff like that in there with single quotes or double quotes, then you have suddenly, and they're not escaped correctly in the export tool, then you suddenly have kind of partially parsed fields which then expand over many lines until the next stray quote is there and so on. That's why I collected a number of tips around this and put it on the website. So on Neo4j's developer web pages, there's a guide to import CSV, and it has some tips and some tools that help you look at the data. But you can actually also use Cypher itself and load CSV to look at the data, because then you see the data as Cypher will see it. And that's actually really nice to see, do I have exactly the number of rows that I want to import? Do I have exactly the number of columns that I want to import? Is the data correct that's in there? Are there some kind of weird things happening, and so on? So that's kind of really interesting and annoying. In general, CSV is kind of the powerhouse of data exchange, because all databases, ETL tools, Office tools can read and write CSV. It's also easy with most scripting languages to read CSV and write CSV. The problem is, of course, that the format is only loosely specified, if at all. So everyone has kind of its own interpretation, how you would skip quotes in CSV, how you would deal with new lines, with trailing new lines, and stuff like that. And that makes it not so easy to agree on something that we support, because someone comes along and says, yeah, but my tool exports the CSV in this way, and why don't you handle that well? Anyway, so there's some tools you can use, as I said, Cypher itself. There's also CSV Kit, which is a Python library, which is really nice. There's also CSV Lint and some other tools, which are also listed on the website. For this address data set that we want to look at, my colleague Rick van Bruggen actually worked on that, and he asked me for some help there. So it's a large kind of joined together CSV file with cities, zip codes, streets, house numbers, and enterprise numbers, entity numbers from the Netherlands. And when you want to import that, then you have the CSV there, and then you would just write Cypher's load CSV statements to create the entities. So entities in this case would be, for instance, if I really want to have a fine-grained data model, I would can do something like, I have a city, and the city has zip codes, which then have streets, or streets are connected to multiple zip codes as well, and then streets have house numbers as well, and then you can put the company, the enterprise, actually at a certain house number. That's the data model that Rick wanted to do. And how does it go? So for load CSV, what it makes sense to create some constraints first, so that later lookup statements are really fast. If you forget that, then it might slow down really a lot. So you can create a constraint or a index for that. So here, these constraints are like primary key or unique keys for city and for zip. And then for the load CSV itself, you just say load CSV, and then if you have a header row that you want to use, then you say with headers, and then you can give it an URL, which could be a file URL, either a local file or absolute directory, could be also HTTP or HTTPS URL. And then you treat each row of this CSV file as a variable, CSV in our case, or we can also call it row or data or item or whatever. And then we use dot notation to access each of the values in the CSV. So each value is passed as string initially, and if you want to change it, there are functions like to int or to upper or split or to float, or you can also use something like substring or so if you want to convert data while reading it in. But initially, everything that's passed is either null, or if it's an empty cell, it's null, or if it's not empty, then it's a string. And you might have to convert it. And so in this case, I use with distinct because this address file has like 2.8 million rows. And of course, there are not 2.8 million cities in the Netherlands. And because it's all the down to the house number, or actually down to the company. And if I do with distinct here, then I get just one row per city and zip code. And so when I run this, then it creates a city. If it's not already there, that's why I use merge, and that's why I have the constraint as well. And same for zip code. So which creates all the cities and all the zip codes at once, which is kind of nice. And then we want to connect them, which we do. Oh, I forgot something. So in the first line, we can also choose to manage transactions in a more granular way. Because usually the whole load CSV statement would run in a single transaction. That means all the changed state for the database that you just created, like all the millions of nodes and relationships, would try to fit into memory. And this is not kind of the most optimal representation. And that's why it would run out of memory if you don't limit that. And the periodic commit kind of just says every X thousand lines of the CSV I commit. So I clean out the transaction state, write it to the disk, and start fresh. And what we do here is actually, it looks the same, except that we don't merge these nodes in, but instead we just match them, we find them. So we find the city by name and the zip code by zip. And then we create a relationship between city and zip code. And you see I've misspelled these here because I wanted to get it shorter so that it fits on this slide. That's something I should change, and I want to demo it now anyway, so I can do it as well. See. So if you look at this, load CSV. So if you look at the address file again, then it looks like this. I have these 13, I think, columns, some of which are not interesting to us, some of which are. And I have the load CSV file, which is called input.cql. And here we have all the stuff that I talked about. So we created constraints, we create some indexes as well, and then we import cities, zip files, we connect the streets, we create entities, and so on. And then I can run this either from Neo4j browser, but actually personally I like to run this from Neo4j shell. So in your Neo4j installation, in the bin directory, or in Windows, when you click on the command line button, then you get a terminal where you can access the Neo4j shell. And Neo4j shell takes either it can connect to a running server, which is also really nice, or it takes a path argument with a database directory. So it could be either a database directory of a server which currently is not running, or just some arbitrary directory on disk. It can take files, which it executes and then exits. And it also can take config. So if I provide config options, a config file, then I can also provide this as well if I want to. So I just delete the old database directory and then I just let it run. And when it runs, then you see it creates a constraint, first constraint, second constraint, and then it takes a few seconds to create the first bunch of nodes. It's, I think, 40,000 nodes or so. So it goes over the whole file, which is in total 2.8 million rows, puts it in, does the two upper and distinct that I mentioned, and now it took 24 seconds to create the 43,000 cities and zip codes, and now it goes ahead and connects the cities with the zip codes, and then it goes to the streets, and so on. Does all of that. And then when it's done, then we can have a look at the data. Okay. So there are some considerations for load CSV, which I don't want to keep from you. So provide enough memory is really helpful, both Neo4j's heap as well as page cache. As I said before, make sure that your data is clean, because otherwise you will get up problems perhaps late in the input process. So it could be the 98% are okay, and then the next line is broken, and then you have an import which is not correctly imported, which is not so nice. It's helpful to create indexes and constraints up front, because then the match operations in your data and in your statements will actually find entities or nodes directly from the index. Otherwise, it has to scan the database. And if it scans the whole database for each row of a CSV file, then you can imagine it will take quite a while. Also, don't forget to use labels for matching, because otherwise it can't find the index that connects to this label. You can use distinct, as I showed you, skip and limit to control the data volume. For instance, if you just want to import a subset of data, but you don't want to split the CSV file, then you can just say with row limit 10,000, and it then just takes the first 10,000 rows. Yeah, you should test with a small batch and use periodic commit when you have more than, let's say, 20,000 rows, depending on how much data you create. And there's a trap which many people run into, which is the eager operation. So Cypher tries to be correct. So that's why sometimes it decides that it has to do certain operations before it can execute the next operation. And to execute all previous operation on a CSV file, it means that it puts in all the millions of lines of data and executes, for instance, the create or match operation. And then it can happen that it runs out of memory. And that's why it makes sense to split up your loading into multiple phases, for instance, to create nodes first and then connect them later. And you can actually figure out if this eager operation happens or not. I also put some links there, so we will share the slides with you after the presentation. And you can use explain to detect it. So I can show it to you actually here in the. Let me just quickly. Look at this data, and if we use a statement like this, where's it? Yeah. So we load CSV, and we take the cities and the zip codes, and we would merge them, and would also merge the city and the zip code directly here. So we do 3 merges, 2 nodes, and 1 relationship. And if I put explain in front of that, I can actually run this in my shell. And then I see in the execution plan of Neo4j 2.3, which looks much nicer than the other ones, there's an eager pipe in between. That means in this step, it loads the 3 million lines of CSV, does the merge, the first merge, and then it pulls in all the data through that, and then it does the second merge. And then it's probably it doesn't have enough memory for that. So if you split it up like this, then it can actually, or should be able to work without eager. Or you split it up in one node per there's still an eager in there. So, but if I split it up in one node per execution, then the eager is gone. Or if I use create instead of merge here, then it's also gone as well. So that's a bit problematic sometimes. And if you run into a load CSV which hangs or so, here it's also gone. Then this could be the culprit. Okay, next in line is the mass data importer, which comes as Neo4j import tool, also in the bin directory, and you can provide it a target. And as I mentioned, it's really memory efficient and scalable, and can be used really nicely for large data sets. This is crime dataset of the city of Chicago. So you can go to a website, which I listed below, download dataset. It's a bit messy, so you have to probably clean it up. You can specify headers directly as part of your CSV file or as separate files, kind of single row files. And those headers contain both ID definitions, data types. They can contain labels and relationship types, or they can also specify which columns to ignore. And then you import it, and then you use it. And it takes, depending on the machine that you run it on, between 30 and 50 seconds to import the data. It's in total, I think, 12 million nodes and relationships, and then another 20 million properties or something like that. And so the data consists of the crime types CSV, which is types of crimes. Beats is police areas. These are probably these here. Then crimes themselves, so the 4 million crimes that happened in Chicago since 2001. And a connection or the relationship CSVs between crimes and beats and crimes and primary types. So these are two small files, and this is a 4 million file. That's a 4 million row file, and that's a 4 million row file. The headers look like this. For the crimes and primary types, which are both nodes, we can provide an ID column, and then because in many databases, not in this case, but in other databases, IDs are overlapping. So if I take IDs from two tables, they actually clash because it's both incrementing primary keys. I can provide a type there or a group there. So this is a crime ID and this is a primary type ID. Then I can provide labels in the file if I want to. I can also provide them externally. And I can also provide other properties as well, and can also do type migration. So if I want to store something as an int or a float value or so, then I can just do colon int or colon float. And same for primary types. So I have the ID again. Crime type is just a property and a label. And actually in my data to make this more sensible, I left out the label. And here I also left out the relationship type in this one. And then for the connections, we have start ID, end ID, and then say which type they are from. So if all my data has non-overlapping IDs like UUIDs, or some table have kind of numeric IDs, otherwise others have alphanumeric IDs, then I don't need these groups, but in many cases it's sensible to have them. And I have a similar set of CSV files for the beats as well. And then for the import tool, I just say, this is my import. I want to import into this directory. Here are my nodes for primary types. I can provide a label at the command line, the colon primary type. If I don't provide it on the command line, it makes sense to provide labels in the CSV file. I can also split out the header, so like the crimes header as a separate single row file. And for relationships, I can again provide the crime type as the relationship type on the command line. And I can also provide it within the file. And having said that, I can demo this as well. So here I have all the CSV files, so I can just say, show me all the CSVs, so first few lines, and then you see what I just told you. Beats are just the areas, crimes, what happened, and when did it happen. Crime beats is the mapping between crimes and beats. Crimes primary types is the mapping between crimes and primary types. Crimes header is my separate header, and primary types is the type of crimes. And if I look how large they are, then I have 3 files with 4 million and in total 30 million rows. And if I run this import script, it tells me I have not a lot of memory on this machine, free. And then it starts to load the nodes, load node properties, see which nodes have a lot of relationships, which don't, aggregate them, do a first pass at relationships, creates them in one direction in the storage files, and then it goes back and creates them in the second direction. It also updates database statistics by doing that, and then it finishes off with writing properties on the relationships, I think. But it does most of this in parallel, actually, so it's actually not that slow. Okay, get done. So, okay, it took a bit longer because the recording of the webinar is running as well. So it created 4 million nodes, 8 million relationships, and 12 million properties. So in total, 24 million records. Okay. And the last thing I want to show you today is a tool I wrote in a few hours, a few weeks ago, which actually takes something I talked about last time, takes relational database information, and when the relational database is still well normalized, then you can, with applying some rules on top of these tables, you can actually create a graph model from that. And I want to show you this as well. So these transformation rules, just quickly to recap them. In general, table become nodes. Table name as node label. Columns turned into properties, except if they're empty, then we don't store them at all. We have to convert some values to other values if Neo4j doesn't support them. We turn foreign keys either one-to-one, one-to-n, and n-to-one into relationships. And we can either turn the column name into the relationship type, or find a better verb, or we can also configure that as well. Join tables, that means tables with 2 foreign keys and no properties, or with no primary key, are turned into relationships, so that's the many-to-many relationships. And columns that are there can be turned into relationship properties. And after I've done that and imported my data, then I can remove some stuff. For instance, I can remove all the technical IDs, especially these auto-incrementing primary keys that many relational databases need to join tables, because in the graph we have actually real relationships to connect nodes. We keep domain IDs. We can add constraints for those or indexes for those for lookup fields as well. And then we just can adjust names to the standard schema that, or the style that Neo4j has, like capitalized labels, uppercase relationship types, and then lower case property names. Okay, and how does it work? It uses JDBC to connect to relational databases. It uses schema crawler, which is a library to extract database metadata. It uses exactly these rules to drive the import. So it extracts the metadata first, creates these rules, and then applies them to the data. It has some means to override behavior and configuration. And it actually uses the parallel batch import API. I wanted to see how fast I can get data out of relational databases. And actually, it turns out that they can't supply the data fast enough for me to write it. And it reads currently tables for nodes and relationships concurrently, so with two connections. And there's this employee database. It's a MySQL demo, and I just have a MySQL server running. And that has this demo database, and I can run the tool against it. The output is a bit weird. So I set this into a database for Neo4j server. So what it does here is it gets the metadata, like primary keys, foreign keys, of each table, so departments, employees, salaries, department employee join tables, department manager join tables, and the titles join table. And then it goes ahead and creates nodes and relationships for all of these. And so the output, it leaves a bit with the parallel batch import output, but you can recognize that from just now. And so it creates these few million entries in a few seconds. So puts it out of MySQL and sends it into Neo4j. And when it's done, then we can actually, come on, look at Neo4j server. So completed in 1 minute and imported, how much? Doesn't say so. Let's start the server. And then we can see from the relational database, for instance, if I look at some employees, I see my employees here. And if I click on an employee or two, depending on which one has some data, we see purple are the employees, green are the salaries, yellow are the titles, and red are the departments. And then I see it also correctly created join from the join tables relationships, and it also created foreign key relationships correctly. This database was a bit tricky because it had a lot of composite keys for primary keys and foreign keys, but actually it worked out really well. And now I can use this as part of my graph, which is really nice. Okay, when you set up your integration between Neo4j and relational databases, there are migration strategies, so you can do all data. So if you want to move to Neo4j completely, you can only take the graph data out of the relational database, so all the heavy joins, heavy join tables, and the data that they need to run can be put in the graph, or you can choose to duplicate the data that you need in the graph, but also keep it in the relational database as well. So several ways of doing that. And in general, it's quite easy to integrate Neo4j in your environment because it connects in a variety of ways with other databases, and both SQL and NoSQL. And then you can run OLTP workloads for your applications, for the end users, and then also do data analytics on your graph model as well. Okay, so there are lots of ways of learning more about all of this. Quite a lot of means, so go to a local meetup, look at the free books that we offer. We have on-site training, we have also online training, and built-in guides in the Neo4j browser help you as well. And here are some resources that you can then also use when you get the slides from us. And I think that's it. Oh no, Graph Connect, San Francisco. October 21st, we run our annual Graph Connect in San Francisco. We want to welcome many, many hundred people to the conference, and right now we still have the early bird registration. So you should grab it as long as it's up. And it's a cool conference with a lot of really, really good people. You can meet a lot of Neo4j people there as well and ask all your questions, learn from others, and exchange ideas, and so on. So it's a really cool conference. I always enjoy going to Graph Connect. And that's it for me, and I'd like to answer some questions now.
Okay, thank you very much, Michael, for this important webinar. So far, we don't have any questions, but maybe give it a few more minutes or moments even for people to type that in. Again, use the dashboard if you have any questions. Type those in or tweet us. Either way, we'll see them and can answer them.
Otherwise, if you don't have any questions, then enjoy, try to look at the resources and reach out to us on the Google group or Stack Overflow if you have questions. And the Git project is on my GitHub repository. So if you go to github.com GEXP, which is my GitHub repository, and it goes to Google Docs, right? Let's try that again. Then you find a ton of repositories here, and one is Neo4j RDBMS import, which you can just check out and run. There's a shell script, and the shell script actually just asks you what's your JDBC URL, what's your schema that you want to import, what's your graph database, and then it goes ahead and does this. And if you want to adapt some things, there's a configuration clause. Right now it's in Java, but I want to pull it out into a configuration, which, for instance, specifies how you want to format table names, what tables you want to skip, what is the relationship type for a certain table, and so on. So you can override all of these or change all of these to make it do your bidding. Patrick wants to know how you would compare graph database with a traditional data warehouse approach. So I think the biggest advantage of a graph database is that you can model all the dimensions that you want to query along as part of your graph model, and you don't have to pre-denormalize your data. So you can just use the high-performance traversal of relationships to take the dimensions that you want to have, take the ranges that you want to have, and dive into the graph. So you use actually the graph model itself as a means of accessing subsets of data. So you kind of create really trees in the graph to handle structured data, for instance, and that makes it really fast to access this kind of data. There are also some blog posts around this, just from our friends and partners, Linkurious. For instance, this one. That's one that I developed with Ralph, who's also a data warehouse and ClickView business intelligence specialist, which is about real-time fraud detection on transaction data for retail systems. Where you can then just say, okay, I want to see which credit cards were used together and which transaction ranges, which products, and so on. And from that, query along all these dimensions really easily. Okay. Ravi Kumar wants to know if there's a table size 1 TB, 1 terabyte in Oracle. So it probably means the table space size. You can use CSV, or you can also access Oracle directly. It depends on what you want to do with data, what kind of data it is, and how your graph model would look like. So if you want to test this, then I recommend you can reach out to us. Just ping us on the Google group, and we can help you get this data imported if you want to. Okay, cool. So, and we're also at the hour now. Thanks a lot for everyone for attending and for your time. I hope you enjoyed it, and we'll send around the recording afterwards.
Yes, we will. Thank you very much, Michael. Thank everyone for attending. Talk to you soon. Bye-bye.